So, do quality work in the future and we'll be good. So today's question is a new derivative shortcut.
Yes.
We won't have to do the definition of derivative until we, at least after we do it. Okay, so check this out. The goal will be to take the derivative of a function that has two functions multiplied, like x squared cosine of x, or e to the x times log of x, or whatever. Okay? It could be any type of product. Now, it would be very logical as a hypothesis to do just what we did for sums. Remember when we did sums, that when we took the derivative of a sum, we just said, oh, you just take the derivative of each piece and add. So the derivative of x squared plus x cubed is just the derivative of x squared plus the derivative of x cubed. And it was 2x plus 3x squared, and we're all good to go. Right? Okay? So it would be logical if I want to take the derivative of, now I don't want to use this to play around with because that's confusing. So instead, I'm going to say, what if I took the derivative on x squared times x cubed? Is it okay to just say, take the derivative of x squared and take the derivative of x cubed and multiply? Well, that's what we did in sum, so it's logical to assume yes. All right, so what is the derivative of x squared?
2x.
And what's the derivative of x cubed? And so if we try that, it feels like we get 6x cubed for a derivative. Is that right? Well, we don't know. But the reason I use this function is because I could know. What should this be another way? Well, what is the derivative of x squared times x cubed? Couldn't we simplify first? Yeah, it is the derivative of x to the fifth. And what is the derivative of x to the fifth? 5x to the fourth. So does it work? No. That does not work. So if you get a product, you can't just say take the derivative of this, take the derivative of that, and multiply. And apparently that's all these notes here. Sorry, those are all what I meant to say there. I forgot that I put that in my notes. My bad. Sorry about that. But the conclusion is you cannot just take the derivative of each piece and then multiply like we do in addition. You cannot do that. It doesn't work. Cool? So, what does work? Well, this is, to me, one of the beauties of math. You know, at our level, somebody who's really good at math is super analytical and fairly deep thinker. But at the highest levels of math, those people are as creative as any English person because they are solving problems way outside the box in a creative way. So let's talk about what the original creator of the product rule, which was probably Newton and Leibniz both, did to get a product. All right, so the question is, how do you take the derivative of a product? We found a way that didn't work, so let's find a way that does work. First thing I did is let's create a function that's just generally a product of two functions, all right? So I'm letting k be two things multiplied. And the question is, what is the derivative of that product, which is what is pretty cool? Now you always start from something that we can all assume to be true, and that is the definition of the derivative. If I want the derivative on k, then using the first definition, I get something like that. K of x plus h minus k of x over h, and take the points close together. You follow?
Yep.
All right, now let's get more into this. Let's replace k with the product. K of x plus h is the same as f of x plus h times g of x plus h. And k of x by itself is f of x g of x, and then h stays h, and the limit stays the limit. Now, for a middle level intelligence like me, I would then get stuck. I'd say, I don't know what to do. Okay? But a creative person would say something like this. Well, let's play around with this a little. And although it's counterintuitive, let's add in some stuff. Now it's counterintuitive because you generally want to make things more simple, not more difficult. But this is actually going to be one step back to take two huge steps forward. The idea is something like this. Let's put something in here that helps us around our roadblock. And the genius step is this. I want you to add in f of x, let's go f of, it could go in two different orders, that's kind of confusing. F of x plus h, g of x is what I want you to add in. Now, even if you're no creative genius, a good math student knows you can't do that. Can I just say, hey, I feel like adding something?
No.
What must you do? You must balance it in some way. And the balance can be a lot of different ways. I could add the same thing to both sides, but I don't want to do that. There's no other side. So we can balance addition with subtraction of the same quantity. And by doing so, I don't know if I helped myself, but at least I didn't break my. You follow?
Yep.
All right. Now then, this is where a little bit of guidance helps. First, there is a reason I'll show you in a minute why I will want those two guys together. So I'm going to rearrange the order. I think you'll agree addition is commutative and subtraction is commutative with negatives. So I can change the order, and this is f of x plus h, g of x plus h, minus f of x plus h, g of x. You follow? And these two other guys, I'm going to put those two together, and I'm going to call that f of x plus h, g of x minus f of x, g of x. Cool. All right. Also, in the interest of space, really, if you were doing this in a proof way, you would have to go very methodically and slow, one change at a time. But if I have a bunch of stuff over one denominator, could I rearrange and separate them over two denominators? Would that be true?
Yeah.
Yeah, I can do that. I usually add fractions in the reverse. I take two different and make it one, but there's no reason I can't go backwards and make one fraction into two, as long as I put them all separately over their derivative, or their denominator. So couldn't I call this over h and this over h? You track it? All right. Now, this is where it gets cool. It's also allowed to say the limit of these two things is the same as the two separate limits added. For example, if I said, what's the limit of x squared plus 4x? Couldn't I just say, take the limit of x squared by itself, take the limit of 4x by itself, and then add later? Yeah. It gets you the same answer. So that's allowed. I can split a limit of a sum into two separate limits. That's cool. So I'm going to do that. The limit and the limit of each of those separate. Follow? And at the same time, again, sorry, I just in the interest of room, this cleaned up with the limit. What is that kind of close to?
Kind of looks like the derivative
Kind of looks like the derivative on f or g?
on F, or G.
G, okay. So because there's a greatest common factor here, could I just put that f of x plus h factored out, and in here do g of x plus h minus g of x all over h? And that, I guess you could say that's over 1 if you like, and that's fine too. You follow me? And what about this at the back side? What does it look like the derivative of? Of f. And what is there a common factor of back here?
G of X.
G of x. So I could factor out a g of x, and inside, these are very intuitive. You might be great mathematicians someday. Okay, so, yeah, someday. You're not there yet. Just keep working. All right, so this, I know this is kind of kooky, but as h goes to 0, what is this approach? F of x. And as h goes to 0, what does this look like?
Oh,
This and that makes what? What is it? We just said, what does this look like? The derivative. So what is this? This and that is g prime. Okay? Plus, now, as h goes to 0, what does g of x go to? G of x, whatever g of x is, but the rest. As h goes to 0, that's f prime. Now that's how you take the derivative of some product k. That's the product rule. It's a shortcut and a good one. The product rule in plain old English is when you want the derivative of a product, it's first function times the derivative of the second function plus second function g of x times the derivative of the first. They basically take turns taking their derivatives, while the other one stays put. Yep. That's the product rule. Now it's a lot of practice. Let's start with just paper and pencil equationing practice. That's the product rule in symbols. If you take the derivative of a product fg, first stays the same, derivative second, plus second stays the same, derivative first. Let's look back at our sample case. We said that when we took the derivative of x squared x cubed, we had a hypothesis that was disaster. We know it's supposed to be 5x to the fourth, and it didn't come out 5x to the fourth. Let's use our product rule now. First stays the same. F means first stays the same, so that's just
x squared.
x squared. G prime means derivative of the second, which is
3x squared.
plus g means second stays the same, so that's
X cubed.
and f prime means the derivative of the first, which is
2x.
we do a little simplifying. Multiplication comes first. 3x to the fourth plus 2x to the fourth is x to the fourth. Okay? All right. Now then, let's show a problem or two. These will go pretty quick on the home. These, once you get good at these take maybe 20 seconds a problem. Okay? So, the first one, do you agree you have a product? All right? So, when we see a product, we use the product rule. First stays the same, so
Yes.
x times the derivative of the second. What's the derivative of x cubed minus 1? 3x squared. Plus second stays the same. X cubed minus 1 times the derivative of the first, and that's e to the x. Now, write yourself a note in your homework. On the homework, or on the notes rather, on the homework you do not need to simplify. Don't need to simplify, but be prepared to do so on a test, especially on multiple choice. Because sometimes on a multiple choice, your answer might be there, but sometimes they say, oh, I did a little factoring. So, for example, on a multiple choice, on a multiple choice, what other algebra could they do there? What might they play around with there to clean that up?
The x cubed minus 1.
Okay, distribute it in or take out an e to the x. If you took out an e to the x, then you might have something like e to the x times x cubed plus 3x squared minus 1 if you wrote it in descending order. You follow me? Okay. All right, so I don't require this step on the homework, but on the test, be ready to do that. All right, would you try that first one, please? Given that product f equals 2 sine x cosine x, find f prime. You do not have to simplify. So here we go. What was your derivative? Let's get some people here. Matt, what'd you say? Derivative on this first one?
2 sine of x times negative sine of x.
Okay. Negative sine of x. Oh yeah, I'm with you. Sorry, you're right. My bad. Go ahead.
Plus 2 cosine x times cosine x.
Love it. Okay. Now Matt did exactly like I did, which is to say he kind of included the 2 in with the sine, as this is the first function and this is the second. Somebody in the last class said I just put the 2 out front and called this f and g and left the 2 out front. Is that okay too?
Yeah.
Yeah, they're the same. If you do that, you get the same exact thing. And so either way is fine. Again, multiple choice, you might have to make a choice, but you'd only see one of the 2. But either one of those is fine. Are we good? Yes?
So why is it plus 2 on the cosine?
Okay, so good question. It's not. If it were something like 2 sine of x plus cosine of x, that would be a distributed 2 that is component to both. But if there's a 2 out front, it is attached to one or the other, but not both. Is that what you're saying? What?
But then why is there the 2?
Here, okay, good question. Because this is first stays the same, derivative of the second. This, I guess you could say, this is second, stays the same, and this is derivative of the first. Either way, when you take the derivative of 2 sine of x, it should also have a 2 in it, so they should both have a 2. You with me? Okay, good question. Any other questions? Cool. Okay, try this one. I remind you, when you evaluate, you first show the general derivative and say, hey, I'm about to put a 1 in, and then in the second step, then you put the 1 in. You never do both at the same time. You show the derivative of t as a function of t, and then you put the 1 in after. Okay, listos? Okay, Lily, what did you say for your first derivative?
I got t squared plus y,
First stays the same, cool.
and then
Okay,
t plus
t plus 9 times 2t, love it. Okay, I agree with the general derivative. Do you all agree?
Yep.
Ms. Brown, when you put in 1, what did you get? 22, do we all agree?
Yep.
Okay, cool. Any questions so far? This is analytical. Remember from the first week I told you I want to understand calculus on 4 levels: verbal, analytical, numerical, and graphical. So let's look at the product rule a different way. Numerical, which is to say, when you hear numerical, just think a table of values. Okay? So given this table, look carefully, you can see that I give you f at 4, f prime at 4, g at 4, and g prime at 4. So lots going on here. Be careful to look at the correct thing. I didn't actually give you a different row of distractors, which would often happen on the AP test, but we'll practice that later. All right. So my first example is find the derivative of fg. That's f times g. That's not f of g. Okay, so don't think of it as a composition, which we haven't done yet. Those can be written that way. This is f times g. All right, so by product rule, the general derivative is, first stays the same, so I need to find f at 4, times the derivative of the second, which would be g prime at 4 plus second stays the same, g at 4 times the derivative of the first. F prime at 4. No matter how good you are, no matter how many times you do this and get comfortable, that's still your first step. If I give that to Ms. Cannon, that's still her first step. She does not go straight to the table. Okay? I don't care how good you are. You always show before you go to a table, hey, this is the calculus. Now I go to the table. So what is F at 4? 2. G prime at 4. -1. G at 4. 5. And F prime at 4. 3. Now we substitute in values, then we simplify. -2 minus 15 is -17. Okay? You with me? And that's FG prime at 4. Okay, would you try the next one? X squared f of x at x equal 4, using that same table, or at least some. I put the 4's in. You could have also just used f and g and then put an evaluation bar at the end. That would be application right there. That would be. Right? Or not quite. Not quite. Okay, Bailey Huss. When you said first stays the same derivative of the second, what'd you get there?
X squared F times X.
Okay, f times x. I like it. First stays the same derivative of the second. Then the second part of the product rule. Let's say, Cole, what's the second part of the product rule? F of x times derivative of the first. Second stays the same times derivative of the first. What's the derivative of x squared? 2x. Okay. And at 4, sorry, I wrote it a little differently, but that's fine. You could have had, I don't know, you probably want 4 writing like this. All right. So if I then put in 4, I get 4 squared f prime at 4. This step would be optional. I just want my work to be clear. Times 2 times 4. So 4 squared can be simplified. It's 16. What's f prime at 4? -3 plus, what's f at 4? 2. And times 2 times 4. I get -48 plus 16. And so what did you get for our final answer? -32. Okay, cool. Let's do one more graphically. Now this one, you gotta be careful. We'll write you a note or two in a second, but this is the product, so I'll need the product rule. Let's just keep it simple. First stays the same as f, and I'm gonna leave out the arguments. Just call it f. Okay, now if you want to write f of x, fine. But what's the derivative of the second? G prime plus second stays the same. That's g times the derivative of the first is f prime. I need to do this at 3. Now, here's where you need to write yourself a note. Be careful. When you want just f for g, how do I use the graph? For example, when I do f at 3 in a second, how do I find f at 3? Go to the x-axis at 3, and then you just go up to the curve. So you just find the y value from the graph. But when you find f prime and g prime at 3, what will I need to do? I need the slope at that. Slope at x equals 3. Not the value, or not the point. All right, so here we go. F at 3, I have a little bit of an advantage in the mine's color-coded, but f at 3, here's the f graph, there's x equal 3. If I go up to the graph and then over to the y, the value of f at 3 is 1. Okay, g prime at 3. All right, now I'm going to go 3, go up to the g graph, and this time, rather than the actual y value, I want the slope of the g graph at 3. What's the slope of the g graph at 3? It's up 1 over 1. It is 1. Okay? Cool. Now g at 3. That means I go up to the g graph, but just report the y value. What is the y value for g when x equals 3? 3. And f prime at 3. That means I go to the f graph at x equals 3 and say, what's the slope? What's the slope? Negative 1/3. Then I clean it up. 1 minus 1 is 0. Okay? You try. If I ask you for the derivative of 2 sine of x f of x at x equals 0, use the product rule because it is obviously a product. Right? Okay, let's first show the derivative. First stays the same means 2 sine of x. Derivative of the second is f prime of x plus second stays the same is f of x times the derivative of the first is 2 cosine of x. And then I'm going to evaluate that at 0. So 2 sine of 0. What is sine of 0? 0. That right away tells me I could probably just call that 0. But what is f prime of 0, just for the fun of it?
Negative 1/3.
It is negative 1/3. Okay? Plus f at 0. What's f at 0? 2. It's the y value on the f graph at x equals 0, which is 2. And what's 2 cosine of 0? 2 times cosine of 0 is 2 times 1 is 2. So your answer is
4.
4. Yay. That's it. So, product rule.
Mr. McMahon?
Yep, hi. How long were you there?
Like a couple minutes.
Oh, cool. Thanks for not interrupting me, I guess. Is the derivative of a product equal to the product of the derivatives?
No.
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 That's no. First times the derivative second. Plus second times the derivative first. Let's go to the homework. Will you get out your fun sheet? Yeah, fun. I don't use the word packet unless I give you 3 or more pages. I feel like it's a fun sheet. All right. The one that students had the most questions with in the last class was the last page. The back of the last page, and then I'll be happy to go back over other stuff. Okay. So, first, I apologize, my hints were separated from the problems themselves, but this is the idea. Where the tangent is flat, the derivative is 0. flat tangent, derivative is 0. Where the curve is increasing, the derivative is positive. This is on the notes before this. So at the bottom of that page 3, maybe? No? I didn't give you these notes?
We have 2 pages.
Oh, sorry, I called for this. Oh, I didn't give you any notes on how to do this. Oh, I erased these. Oh, no, I used the table there. I kind of changed it. I see. This looks different on yours. Sorry, this was from last year. I improved it, but that's okay. The idea here is this, actually. I want to walk through the big ideas on not these two, but just go right below it. This is the best place to start in terms of the strategy, all right? So do you see where I'm at? On 71?
Yes.
Okay, this is a function. These are examples of original functions. These are the derivative of some function. Question is, can you match the derivative to the original? This is the state of mind, and it is very much a state of mind. On the original function, draw tiny tangents. Okay, so on this, you got a small positive. But at that point, the slope is flat, which means the derivative is 0. That's a very important point. Then the slopes go negative. Then here they go 0 again, positive, and then it's tempting to say, oh, that part doesn't matter, but it does matter because that's another place where the slope goes 0, and then afterwards it's negative. So when you go to find the derivative, you want to find a graph that has 1, 2, 3 zeros. Which graph has 3 zeros? And it is 3. What about the sign stuff? Does it go positive, then negative, then positive, then negative? Yeah, if a derivative is positive, it's above the axis. Then it's 0. If the derivative is negative, it's below the axis. Then it's 0. And if the derivative is positive, it's above the axis, then it's 0, and then negative. So in terms of matching the behavior, it's graph 3. And that's the state of mind. So let's go to graph B. Positive or negative slopes? Positive, bigger positive. Here, slope is 0, negative, negative. Which graph has exactly 1, 0, and is positive before that 0 and negative after? 1. You can see that this has 1, 0, and is positive before and negative after. So this is graph 1 is the derivative of graph B. Now, by elimination, obviously, we could know the final answer, but let's exercise our mind. Positive slope, 0. Little bit, and a very little bit of negative slope, 0. Positive slope, which has 2 zeros and a little negative in between. Well, obviously that's graph 2. You tracking? All right. Now, that is really the only way to think through that middle example. Go up to that first example now. I actually have 2 strategies here. First of all, I could do that same idea. These are the functions and these are the derivatives. This, positive, 0, negative slopes. Which of those has 1, 0 and is positive before that 0 and negative after? 3 is positive, 0, and negative. When I say positive derivative, I mean the graph of the derivative is above the axis. When I say 0 derivative, that means it crosses the x-axis. The negative is below. So this is graph 3. Okay? This guy, slope is always positive. So you're saying that slope is never 0? Yeah, I agree. It's never 0. In fact, it's always constant slope. It's always the same slope. Which of those is always positive, never 0, always the same number? 1. Okay? Graph 3. It looks like the slopes go positive, 0, negative, 0, and positive. And so which has two zeros and then goes positive, negative, positive. That's 2. Cool. And the last one goes like positive, 0, negative. Which one has positive, 0, negative? 3. All right. Now, I told you I have 2 strategies for this. That is the same. What does a tangent slope look like? But let's use power rule kind of thing. Equation-wise, what does this look like? Parabola, negative x squared. So what's the derivative of negative x squared? Negative 2x. Does this look like a line with negative slope?
Yes.
Okay. This looks like a constant, x to the first. Whatever is here. What's the derivative of x to the first? 1, x to the 0, or just 1. Okay? What about the derivative of x cubed? 3x squared. That makes sense that it would have a derivative. It's a parabola. My question is, how can these guys both have the same derivative? How can that be? 2 totally different functions have the same derivative? How? Both parabolas, different by what? A constant added, right? So this you might say this is something like negative x squared plus 2, and this might be negative x squared minus 2, but when you take the derivative on that, what happens to that constant? It goes right. So yeah, they have the same derivative because they have the same shape. Where the derivative, where the shape is, doesn't matter. Okay? Now, this then you have 2 skills. You could say, what are the derivative tangent slopes? Or you could say, what are the powers? Now, notice on this one, these graphs are whack. I don't know what equations these are. So that's why I didn't use that skill here. You have to know derivative skills. Okay? Let's go here to this guy. You see it? Okay. Now this, in black, is the original function f. Sometimes they will ask you to draw the derivative on the same graph or in the same space. So here, what's the slope here? I'm going to let red be the derivative. 0. So where did I graph the derivative? If at 0 the derivative is 0, isn't that here? And at 1 the derivative is 0, isn't that there? And at 2 the derivative is 0. 3 the derivative. In fact, at all those points the derivative is 0. Okay? What about in here? What's the derivative here? One half, isn't it? Up 1 over 2. So you're saying that at all these points the derivative is 1 half, here, 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 and all the in between. So there. That is a constant. Derivative is always the same there. Is the derivative always the same here?
No.
So it won't be a constant like these horizontal bars. It'll be something different. At 5, what ballpark? What does that slope look like about? Just estimate. 2. Okay, so at 5, I'm going to record a slope at 2. What about at 7? What's the slope? 0. Between 5 and 7, what were the slopes then between 5 and 7? Did they go straight from 2 to 0 with nothing in between, or did it get gradually less, gradually less, gradually less, gradually less? So like that. Okay? Then these slopes, little negative, bigger negative, bigger negative. So what are they going to look like right of 7? Negative is below the axis. Does that make sense, though, that the derivative of a negative x squared would be a negative line? Yeah. Negative sloping line. These bars do not, that's a great question. I'm so glad you asked. Okay, so those bars do not connect, and here's why. Do the slopes here go from 0 to 1/2 smoothly? They just go straight from 0 to 1/2, nowhere in between. So there is no place where the slopes are a little more, like 1/4, and a little. So no, they do not connect. There is no slope of 1/3 or 1/5 or 1/10. Right? So good question. That actually goes to the question of differentiable. You would say the derivative doesn't exist at 3, so those should actually be open circles and open circles, but that's for another day. Okay, don't worry about that. Just worry about the shape of the graph. All right, then the last one, this one. So I feel like I understand calculus pretty well. I didn't know what to do here. I mean, this is kooking me out. So let's replace this with, let me tell you this. One of those is the function. One of those is the first derivative of that function. One of those is the second derivative of that function. Tell me which is which, all right? So let's approach it this way, and let's do it together, shall we? So I don't know which one this is, so I'm just going to start saying, what if I took the derivative of this? I'm going to do red derivative slopes. Positive, 0, negative, 0, positive. Is there a graph next to it that has positive 0, negative 0, positive, or 2 zeros? Yeah, it feels like C. So what does that mean then? That C is the derivative of A. Now that actually is not done because that could either mean this is F and this is F prime, or it could mean that that's F prime and this is F double. So we don't know that yet, so we need to do more, okay? What do you want to also investigate the slopes on? You want to take the slopes of this bad boy or this bad boy? B? Okay, so if I did slopes here, the slopes are negative, 0, positive, 0, negative. Is there anything else with 2 zeros? Well, yeah, this has 2 zeros, but does it go negative, positive, negative? No, this goes positive, negative, positive, so this doesn't have a derivative. This doesn't have a derivative. What does that mean it must be? Does that mean it's F or F double? That means it's F double. This is F double. Okay? So is that enough or do I need to continue? What does this need to be then? Actually, let's just go here. 0, negative, 0, positive, 0. Is there anything you see with roughly 3 zeros at the very edges and a 0 in between? Yeah, this looks like the derivative of this must be B. So, tell me, what do we got here? This is F double, we said. This must be F prime, and this is F. Okay? And I don't know if the last ones, do you want to look at the graph sketch, the derivative sketches of the last ones? Okay.
Good morning, Dublin Jaguars. Please rise to the Pledge of Allegiance. Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. The college fair on September 11th is during lunch in the main gym. We will allow juniors and seniors to attend the fair first, and all other students can attend the fair when an announcement is made. There will be candy in the round to win cool prizes at the end of the day. Don't worry about dinner tonight. Please support the boys' tennis team by going to school in the Cool Shopping Plaza at Camden and Wadsworth tonight from 4 to 8 p.m. Please mention that you are supporting the team when you check out. Thanks so much for your support. Go Jacks! Attention all students. On Wednesday, September 11th, we will be holding our annual college fair. There will be in-state and out-of-state college fair during lunch, and we will have an event in the evening full of breakout sessions to provide information to you and your family about the college process. All are welcome and
Do you agree these approach linear out here?
Wednesday.
Yeah.
So roughly slope of positive, maybe even a constant, like maybe 1.
Today, 2 colleges will be in the
Okay?
conference.
So at all these points,
With Northwest
the
University
slope is
of
1.
Illinois. Their lakefront campus is ideal with a year-round sailing center and ice rink. A fun fact,
Here,
Northwestern has a nation's largest
slopes start to get flatter and flatter, so they gradually turn from there to 0. Then afterwards they go slightly negative, more and more negative, approaching
You must return them as they are your responsibility. If you do not return them, you will be given a warning. If you get 2 warnings, you will not be allowed to send out a Chromebook for the rest of the year. Many of you already have.
Yeah, this is not a sharp turn, it's a gradual turn, so that's why these pieces are joining.
Coaches are there to teach and develop your skills.
Any others? You want to talk about 1 or 3?
It's never too late.
Okay.
Tomorrow, college will be from Johns Hopkins University from Baltimore, Maryland, and Vanderbilt University from Nashville, Tennessee. Johns Hopkins will be here only during first lunch. Students who have second lunch will miss 30 minutes of their 4th-hour class. Make sure you get a pass from counseling. In addition, Vanderbilt University from Nashville, Tennessee will be here during 7th hour. Both are highly selective. Remember, a face with a name shows that exhibit interest and can give you an advantage in the application process. Junior high students, today 8th graders with last names beginning A through K will be doing their needs assessment in the auditorium. Please sign up with one of your teachers, and then you will be called over the intercom about 2 o'clock to report to the auditorium. 8th graders L through Z will be tomorrow, Wednesday and Thursday will be celebrated. Dazzling Jags. The Jaguar boys soccer team played their heart out last Friday night at Lakewood Memorial Field against 5A powerhouse Chatfield before becoming 2-1 and going 2-1-1 on the season. Scoring for the Jags was Julian Castro on an assist by Aiden Cushing. Colin McCabe was his usual awesome self with 10 saves and goals. Please support our boys as they expect them to take over the Centaurus High School this coming Friday, 5 p.m. at the North Area Athletic Complex. Help is Friday the 13th at Lucky Day for our Never Say Die boys. Go Jags! Congratulations to the girls softball team. They're on a pretty exciting streak after beating powerhouse 5A Ralston Valley on Saturday 9-4. Good luck Tuesday against top 5 ranked Brookfield.
Hi, Dublin Jaguars. This is Mr. Willie. In this mission,